Hello and welcome to my channel. In this tutorial I'm going to talk about process sigma level, what it is, how to compute it and why we need it. And I will also talk about defects per million opportunities, DPMO, how to compute short-term DPMO, difference between short-term and long-term DPMO, and how to compute long-term DPMO. Let's talk about process sigma level. Process sigma level is the number of standard deviations between the mean and specification limit, upper or lower, given that the process is centered within the specification interval. The formula is half width of specification interval over standard deviation. Now let's look at the example and calculate the sigma level of a manufacturing process of a part with respect to the part thickness specifications. The part thickness is normally distributed with a mean of 47.5 mm and standard deviation of 1 mm. The thickness specifications are 45 to 50 mm. The figure on the right depicts our process. You can see the normal probability curve for our random variable thickness. The black solid line marks the mean, the black dashed lines mark standard deviations, and red solid lines mark specification limits. You can also see that the distribution is centered within the specification interval. So the sigma level is 50 minus 45 divided by 2, which is half width of specification interval, divided by 1, which is our standard deviation. So sigma level is 2.5. Please note that the process sigma level is determined with respect to given specifications. What it means is that if specification limits change, you will have to recalculate the sigma level of a process. So why do you need the process sigma level? It allows you to easily compute the defects per million opportunities, DPMO, which is a useful performance measure of a process. So let's calculate DPMO. For now, just ignore the word short-term. On the next slide, I'm going to explain the difference between short-term and long-term DPMO. Then you will understand why this DPMO is a short-term DPMO. But for now, it's just DPMO. Okay. The equation for DPMO is probability of having a defect multiplied by a million. Probability of having a defect is the sum of two probabilities. Probability of t less than lower spec limit and probability of t greater than upper spec limit. And you can see on the graph these two probabilities are the red areas below the tails. Since the process is centered within the specification interval and the normal distribution is symmetric, probability of t less than lower spec limit is equal to probability of t greater than upper spec limit. In other words, red areas are equal. Since the total area under any probability curve is 1, probability of t greater than upper spec limit is equal to 1 minus probability of t less than or equal to upper spec limit. Use equation 2 and 3 to rewrite equation 1 as 2 multiplied by 1 minus probability of t less than or equal to upper spec limit multiplied by a million. Since the process sigma level is 2.5, the z value for the upper spec limit is also 2.5. So we can rewrite equation 4 as 2 multiplied by 1 minus probability of z less than or equal to 2.5 multiplied by a million. Now we can use a table to find probability of z less than or equal to 2.5 and plug it into equation 5. So let's go ahead and take a look at the table. What you see is the table of areas under the standard normal curve. The standard normal distribution is the normal distribution with a mean of 0 and standard deviation of 1. A random variable with a standard normal distribution is typically denoted with the letter z. As you can see from a diagram, all the areas are calculated to the left of a particular z value. So now let's look at the table itself. The first column is the z value to the 10th decimal place, and the top row is the 100th decimal place of a z value. So to find the area corresponding to a z value, you have to find the row and the column for the z value, and the intersection is the area you're looking for. So in our case, the z value is 2.5. We find row and the column for 2.5, and the intersection is 0.9938. So now let's go back and plug this value into the equation 5. We plug the value into equation 5 and we get 12,400. So the short-term DPMO is 12,400 defects per million opportunities, and it is the best case performance of our process. Now I will explain why this DPMO is a short-term DPMO and why it is the best case performance. Short-term variation is computed from sampling data. Sampling data is collected over a short period of time, typically a few months, and does not capture all sources of random variation of a process, because some sources of random variation are time dependent. Long-term variation, on the other hand, includes all sources of random variation, but its computation is not feasible. Thus, a long-term standard deviation is rarely known. Please note that long-term variation must not include non-random sources, and this is a very typical misconception. Short-term variation is always smaller than long-term variation. Thus, a short-term performance measure such as DPMO represents the best case process performance, whereas a long-term performance measure represents the worst case process performance. To compute a process performance measure, short-term or long-term, we use a short-term standard deviation. However, computation of a short-term performance measure requires the process probability distribution to be centered between the specification limits, whereas a long-term performance measure requires the process probability distribution to be corrected by shifting the mean by 1.5 sigmas in either direction. However, if a long-term standard deviation were known, it would be used without shifting the mean. Thus, this shift compensates the use of a short-term standard deviation instead of a long-term standard deviation. Now, on a previous slide, we calculated the DPMO, and I've mentioned that it was a short-term DPMO. And I've also mentioned that it gave us the best case process performance. Well, any short-term process performance measure gives you the best case scenario. It was a short-term DPMO because first we used a short-term standard deviation, and second, our distribution was centered. Now let's go ahead and calculate the long-term DPMO. To compute long-term DPMO, first we have to shift the mean of the distribution. As you can see from the figure, the mean of the distribution has been shifted by 1.5 sigmas to the left. We'll use our familiar formula, probability of having a defect multiplied by a million. Again, probability of having a defect is the sum of two probabilities, probability of t less than lower spec limit and probability of t greater than upper spec limit. As you can see from the figure, the two red areas are not the same. Thus, the probabilities are not equal and will have to be calculated individually. Since the process sigma level is 2.5 and the mean is shifted 1.5 sigmas to the left, the z-values for the specification limits are, so the z-value for the lower spec limit is 2.5 minus 1.5, which is a 1. Take a negative of that, you get minus 1. The z-value of the upper spec limit is 2.5 plus 1.5, which is 4. Now we'll use these z-values to rewrite the probabilities as follows. Probability of t less than lower spec limit is equal to probability of z less than minus 1, which is equal to probability of z greater than 1, which is in turn equal to 1 minus probability of z less than or equal to 1. Probability of t greater than upper spec limit is equal to probability of z greater than 4, which is in turn equal to 1 minus probability of z less than or equal to 4. So let's go back and use our table to calculate the probability of z less than or equal to 1 and probability of z less than or equal to 4. You can see that in this table the z values go only up to 3.9. You can also see that the probability of z less than or equal to 3.9 is much greater than the probability of z less than or equal to 1. So 1 minus probability of z less than or equal to 3.9 will be much less than 1 minus probability of z less than or equal to 1. So we are going to ignore probability of z less than or equal to 4 and we'll just calculate the probability of z less than or equal to 1, which is 0.8413. So the probability of t less than lower spec limit is 1 minus 0.8413, which is 0.1587. We multiply this value by a million and we'll get 156,700 defects per million opportunities. This is a long-term DPMO and it gives us the worst case process performance. You can use the same procedure outlined in this tutorial to calculate short-term and long-term DPMO for different sigma levels. I did calculations in Excel and as you can see I included Excel formulas in the table. On that I would like to finish this tutorial and thank you for watching and I hope to see you in my next video.